Hi everyone, we're continuing with lesson 18 on binomial distributions. This was the problem that we did last time. Later on in part F, these are handwritten notes and these are notes that we'll cover much later on. They're optional for now. So I'm going to go over the handwritten optional notes backwards. So again, part F, we're not going to deal with right now. Part C, you won't have to know for the exam, but it's one of the most beautiful things in math. So let's go to more beautiful websites. Pascal's triangle, which is really optional. And folks, believe it or not, this here is Pascal's triangle, one of the favorite games on The Price is Right.
I want you as Gordon the Elf to ask Rich what we have for Christy today.
Rich, what do we have for Christy today?
Christy, you're going to play Plinko for a chance to win up to $50,000.
Happy birthday, Scott. Come over here, Christy. Scott's our PA. He makes the least amount of money, so we like to get to come on TV and get a little thrill. That's Scott. That's in lieu of money from CBS. That was a little gift from CBS in lieu of money. Here's the Plinko chip, worth up to $10,000. That's more than we pay Gordon that's more than we play Gordon the elf all year long. Up to $10,000, and you can win 4 more chips worth up to $10,000, so almost $50,000 if you know anything about these prizes. What's the first prize? Rich Fields.
All right, first, your Christmas decor just got a little more elegant with his hand-painted snowman figurine.
Now, it's not $68, but the price starts with a 6 or ends with an 8. What is it? It starts with a 6 or ends with an 8.
Ends with an 8.
Ends with an 8. Give her another Plinko chip, please. Rachel, yes. Rachel the elf has gotten you another Plinko chip. Rachel is Santa's little helper today. What's the next prize?
So basically she accumulates chips, and this is what she does with them.
Got to do one at a time. You're going to put them flat against the wall, let it drop. You want $10,000 right in the middle here. That's what you want to get 5 times. Just put it up flat against the wall and drop it whenever you're ready. There you go. Come on down. Come on down to 10,000, 10,000, 10,000, 10,000, 10,000, 10,000. Oh! So close. Right there. That's where you want it. That was really close.
True.
Really close. Really close. There you go. Right down the side. Back in the middle. Back in the middle. There you go. Stay in the middle. Stay in the middle. 10,000, 10,000, 10,000. Do it one more time, right there. That's where you want it. She's trying to figure out where she put it the last time. It's like bowling, isn't it? You just got to figure out where you put it the last time, and it'll all be okay. $10,000, $20,000, $20,000 so far. One more time. Don't lose your mojo, Christy. I don't know. I can't remember. Somewhere right around there. $20,000. 20,000. Here it comes. Back in the middle. Back in the middle. Oh no. $100. 20,100. This could be a record breaker. You get that extra $10,000. You got one left. What's the record? The record's 23,000. You get that 10,000. You're going to set a record for Plinko. If you get the 10,000 again, you're going to set a record for the most one on Plinko. Here it comes. Oh, bounce left. Stay in the middle. Stay in the middle. Come on down. Get in the middle. A new Plinko record. A new Plinko record. $30,100. Christy, come on down here. A new Plinko record. 36 years of Price is Right. $30,000 for Christy. That's what the most anybody ever wants for Plinko. We'll be right back with more Price is Right after this.
So that is the Pascal's triangle. Plinko is Pascal's triangle. Let's go to this great website, mathisfun.com, which does a great job with Pascal's triangle. So how is Pascal's triangle constructed? You might remember this from your algebra class. So you start off with a tent of ones. So you have ones along this edge and ones along this edge, like a pyramid. Now, every time you have 2 consecutive numbers, they give birth to their son, their sum. So for example, here, the 1 and the 3 give birth to a 4. So up here, 1 and 1 give 2. Over here, 1 and 2 give 3. 2 and 1 give 3. And then here, 1 and 3 give 4, as they show. 3 and 3 give 6. 3 and 1 give 4. By the way, one of the properties of Pascal's triangle is that it is symmetric. If you draw an axis here, you see the left and the right mirror each other. The left half and the right half mirror each other. And Pascal's triangle is gorgeous. There are so many patterns. Of course, you have ones along this diagonal. You have the positive integers on this diagonal, the triangular numbers. Imagine dots like 1, 2, 3, right? On this diagonal. Again, we have symmetry, left side and right side. If you add up the sums, and we'll see why this is true, 1, 2, 4, 8, 16, and so forth, powers of 2. And there are reasons for that. Surprisingly, exponents of 11 are hidden in here, powers of 11. The Fibonacci sequence, remember, 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3 equals 5. Each successive Fibonacci number is the sum of the 2 prior Fibonacci numbers. It's a famous sequence, and it's also hiding in Pascal's triangle. If you shade in all the odd entries, and you do it for many rows, you get the Sierpinski triangle or gasket. It's this thing, which is a famous creature in chaos and fractal theory. The idea that basic rules lead to these elaborate, complex patterns. Okay, now we saw the powers of 2 before, and this kind of explains why. For example, consider 3 flips or tosses of a coin, fair or not. All right. Well, how many possible sequences of 3 heads or tails can we have? Well, we have 3 flips or 3 positions. Each position can be a head or a tail, right? So we have 2 possibilities for the first flip, 2 possibilities for the second, and 2 possibilities for the third. 2 times 2 times 2 is 8. Now, Pascal's triangle, let's look at this. 3 flips or tosses of a coin, fair or not, all right? Notice there's only one way to get 0 tails and 3 heads, 3 ways to get 1 tail and 2 heads, 3 ways to get 2 tails and 1 head, and only 1 way to get all 3 tails. These are the numbers in Pascal's triangle on row number 3. Bear in mind, when you look at Pascal's triangle, row number 0 is on top. So row number 0 has the 1. Here's row number 1, row number 2, row number 3, and so forth. You can look at the second number in the row to see what row number we're talking about. Now, it turns out that Pascal's triangle is this list of binomial coefficients over here. N choose K, or NCR. Do you remember those numbers? Remember 52 choose 5 or 52 C5, the number of possible poker hands from a deck of 52 cards? That's 52 choose 5. That's way down in the table in Pascal's triangle, but it's there. So basically, if you're like Vanna White on another game show, if you flip these binomial coefficients around, these NCR values, you're going to get Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and so forth. Here are the first 15 lines of Pascal's triangle, rows 0 to 14, and the ancient Chinese knew about it. I want to go back to why it is that these binomial coefficients, these NCR numbers, the number of combinations of n items taken r at a time, like poker hands, why they correspond to Pascal's triangle. All right. Well, again, this is why it's Plinko. Let's go back to this Plinko board over here, this Pascal's triangle. All right. In fact, I'll go to the very top. All right. So how many ways are there to hit this pin over here? Imagine that each of these squares corresponds to a pin. How many ways are there to hit this pin over here? 3 choose 1 or 3. Left, left, right, left, right, left, and right, left, left. We're imagining these falling chips. How many ways are there to hit this pin over here? Only one way. Left, left, left. Well, there's one way to hit this pin and 3 ways to hit this pin. How many ways are there to hit this pin? 1 through here, and then go right, 3 through here, and then go left, 4 ways to hit this pin. So the number on each of these squares these numbers in Pascal's triangle, they correspond to the number of ways that the chip can hit that pin. Let's go back here. Why is this 3 choose 1? 3 choose 1 is 3, all right? So 3 drops, n equals 3. A right is a success. Right is a success. So left, failure, right, success. That's one way to get 1 success and 2 failures. Left, failure, right, success, left, failure. Again, another way to get 1 success and 2 failures. 1 right, 1 success, 1 left, a failure, another left, a failure. So how many ways are there to get 1 success and 2 failures out of 3 trials or 3 drops? 3 ways, 3 choose 1. So that's an example of why Pascal's triangle is a table of these binomial coefficients, the number of combinations, NCR, n items taken r at a time. Again, 52 choose 5 is way down here, about 2.6 million. At the very bottom, again, the Plinko board. It's called a quincunx. So let's say that it's 50-50. P is 0.5 in a binomial distribution. Let's speed it up. Here, n equals 6, p equals 0.5. And we're looking at what a binomial distribution where n equals 6 and p equals 1/2, what that histogram would look like. And take a look at this. It's looking more and more bell-shaped. What if we up it to 15? N equals, wait, let's restart this. N equals 15, p equals 0.5. Sped up, looking down there. N equals 15, p equals 0.5. Binomial distribution. Again, a right is a success, a left is a failure. Each drop is a trial, which means that these numbers here correspond to the number of successes. If you're a student who gets all 15 questions correct on a true-false exam, for example, then you'd be in this bin over here. Not very likely, though. And again, it looks more and more bell-shaped. All right. And they explain the quincunx over here. Again, it's a great website. Great website. Okay, and a normal distribution approximates that. But Pascal's triangle is absolutely gorgeous and is relevant to the binomial distribution, as we'll see in the next video.